Welcome to the third part of acid-base disorders. This is Dr. Patel again. In this part, we are going to discuss and solve 6 cases of real acid-base disorder. So let's dive into it. So our first case is 48-year-old man who presented to emergency department with sudden onset right-sided pleuritic chest pain. Pain is such that he has a difficult time taking a deep breath. His vitals stable, pulse 112, respiration elevated at 22. And this is the ABG that we got. So as you can see here, so 7.46, so high pH, and then carbon dioxide is 32, so went down by 8 from 40. So let's multiply that by 0.08. So it is going to be 0.008, sorry. So it's going to be 0.06. So that means, so that was the exact number. As you can see, pH went up by 0.06. So that means that alkalosis was contributed by washing off of carbon dioxide. So it is compensated. So we cannot calculate anion gap. So there is alkalosis and it's respiratory alkalosis. So that is information that we got from here. So it could be from so many different causes. Let's calculate AA gradient. Let's calculate big A first. So big A, as you all know, 150, because this patient is on room air, so 150, and then you are going to divide PCO2. How much is PCO2? PCO2 is 32, and you divide that with 32, divide that with 0.8, so which is going to be 40. So 150 minus 40 is going to be 110. So AA gradient is markedly elevated. So normal AA gradient is divided by 4 plus 4. So this patient should have normal AA gradient of 16, but this patient has a very high AA gradient. So this patient, if this patient has SIV, then what are the implications? So such a hypoxemia, you are thinking about PJP pneumonia, and then such a high AA gradient and hypoxemia, they also made the indication for steroid users in those cases. So that's how important AA gradient calculation, as you can see here. Yeah, I think we talked about everything in this slide. So let's solve case 2 together. 24 white woman with a long-standing history of severe asthma. She is admitted with severe exacerbation. So these are the electrolyte and this is ABG. What is the acid-base process here? So as you can see here, pH is 7.51. So high pH is alkalosis. And then how much is the CO2? CO2 is also down. So most likely it is respiratory alkalosis. Then let's calculate how much is the delta. Delta is, so carbon dioxide went down by 15 into 0.008, 0.008. Since it is acute, so that's what we are going to take. So it is going to be how much? That is going to be so that's the number. So that is a change in pH. So that's exact change in pH we can actually see here. So that alkalosis is secondary to washing off carbon dioxide again. So 6 hours later, the picture changed. And this is the BMP and ABG. Let's solve this. So pH went down to 7.24 and PCO2 of 43. So PCO2 went up from 40 to 43. So that is delta of 3. So 3 times 0.008 is going to be how much? So that is going to give 0.02. So if that was PCO2 change, the pH should go down just up to 7.38, but here pH is 7.24. So there is a second process causing acidosis, and which is metabolic acidosis. So let's calculate anion gap. So anion gap, in this case, you add chloride and bicarbonate, so it is going to be 119, and then so this is 136. So anion gap is 17. So there is additional acidosis. So this patient has two acidosis. One is respiratory acidosis. So remember, high carbon dioxide or respiratory acidosis means there is a problem in the ventilation. So it's very important to see this patient in person right away. You cannot miss on this. So respiratory acidosis kills the patient right away, but it's very easy to correct. Once they get intubated, they are put on ventilator, all the defect is all gone because ventilator does the job. So this patient has respiratory acidosis, so needs immediate attention. Number two, this patient has a anion gap metabolic acidosis. Now you need to find that out. So next step is going to be checking lactic acid. So let's solve case number 3. 54-year old black woman with a history of diabetes, ischemic heart disease, chronic congestive heart failure, which is compensated on medication. Current medication include Lasix, insulin, enalapril, and potassium. So this is the BMP. What is the acid-base disturbance, and what is the likely explanation, and would additional information helpful like ABG? So let's start with the anion gap calculation. Anion gap is, so we add chloride and bicarbonate, so it is going to be 128, and so 136 minus 128, so 8, anion gap of 8. And then this patient has a bicarbonate elevated at 29, so patient has most likely contraction alkalosis from diuresis, over diuresis. So that will explain this increase bicarbonate. So would additional information be helpful? Answer is no, because this patient, this BMP profile is very well explained by the medications and the history that patient has. Um, so let's solve question number 4. 70-year-old African American man who presents with long-standing shortness of breath on exertion. His previous provider prescribed home oxygen therapy. You repeat ABG to assess his current status. So pH is 7.37, which is less than 7.40, so acidosis. And then what is the carbon dioxide number? Carbon dioxide number is elevated. So carbon dioxide is elevated by so 49, right? So 49 means delta of 9 into so this is chronic, so you are going to do 0.0003. So that means 0.02. So that change in carbon dioxide is going to bring that pH down to 7.38. So close enough. So it fits chronic picture. So looks like that increase in carbon dioxide is contributing to that acidosis. So chronic respiratory acidosis, very likely. But look here. Oxygen saturation of 97%. I think that's a really high number. Any number more than 95. Remember, you don't need pulse ox more than 95 in any conditions. Actually, supplementing oxygen, keeping that oxygen number more than 95 has shown to increase the morbidity in people with, even in the people with stroke, even in the people with ischemic heart disease. So, and in this case, actually giving too much oxygen is doing patient the harm. It is causing them to make more carbon dioxide here. More oxygen you give, more carbon dioxide they make. So it is contributing to chronic respiratory acidosis that patient has. So what you are going to do now, you are going to re-evaluate the oxygen requirement. Whatever oxygen level this patient is on, you are supposed to go down on that oxygen by doing that 6-minute walk test, first starting with the rest oxygenation. So that is the information that you are going to get next. So let's solve case number 5. So this is a 50-year-old female with lethargy and confusion. As you can see here, ABG shows pH of 7.21, carbon dioxide 60, and this is BMP. So what kind of acid-base disorder this patient has? So let's solve this case. So starting with this 7.21, so acidosis with high carbon dioxide of 60, so 20 more, 20 into 0.008, so that is going to be 0.16. so with this carbon dioxide pH is supposed to go down by 0.16, which is 7.24, but this patient has more acidosis than you expect from that carbon dioxide, so that means there's additional process, most likely metabolic. So let's calculate anion gap. So anion gap in this patient is 132 minus, you combine 88 and 22, which is 110. 132 minus 110 is, so anion gap of 22. So how much is the normal anion gap? Normal anion gap is 12. So this patient has how much? This patient has 22 minus 12. So that is a delta. That is delta is 10. If there is a delta of 10, they are supposed to have low bicarbonate. The bicarbonate is no longer 24. The bicarbonate should be 24 minus 10. So that is expected bicarbonate. But how much bicarbonate this patient has? The bicarbonate in this patient is 22. So patient has more bicarbonate than expected from this degree of acidosis. So that means, so this patient who was supposed to have a bicarbonate of just 14 has 22. So that means patient has a metabolic alkalosis. So very likely this patient vomited. So this patient has a metabolic acidosis, anion gap acidosis, and most likely patient vomited and caused metabolic alkalosis, and patient has a respiratory acidosis. There is another way to calculate respiratory acidosis too. That is Winter's formula. So let's apply Winter's formula. Here bicarbonate is 22. Bicarbonate into 1.5 plus 8 plus minus 2. So that is a Winter formula. So this patient, 22 minus 1.5 is going to be 33. 33 plus 8 plus minus 2. So 33 plus 8 is 41. 41 plus minus 2. So with this um, bicarbonate, we anticipate carbon dioxide number to be somewhere from 39 to 43. How much carbon dioxide this patient has? This patient has 62, so has more carbon dioxide than expected from this bicarbonate level. So that means patient has a respiratory acidosis. So this patient has anion gap acidosis. So let's say if this patient has a blood sugar of 400 and beta hydroxy beta rate more than 3, then you have a diagnosis of DKA. So you would like to go through anion gap acidosis, the causes of anion gap acidosis, one by another, and try to paint the clinical picture. So metabolic alkalosis and respiratory acidosis. This patient has triple disorder. So let's solve case number 6. 65 male presented with worsening shortness of breath, on exertion and orthopnea over 1 week, current smoker, ABG on high flow supplemental oxygen of FiO2 of 50%. So remember, a formula is going to be different here, and this is the ABG number. Base excess 11, bicarbonate 44. What kind of acidosis patient has? Calculate AA gradient and what is the etiology. So let's solve this together. So expected bicarbonate in a chronic compensated respiratory acidosis. So this patient has acidosis and high what you call carbon dioxide. So basically carbon dioxide is up, is very high here. As you can see, went up from 40 to 100. So the formula that we have is expected bicarbonate in these people is going to be 24 plus every 10 increase in PaCO2, bicarbonate is supposed to rise by 3. So this patient had a rise by 6, right? 40 to 51, 50 to 60 is 2, so it is 6. It went up to 100. So 6 rise, and 6 times 3 is going to be 18. 18 plus 24 is around 42. So how much patient has? Patient has bicarbonate 44. So close. So that bicarbonate number is well explained by that rise of what you call carbon dioxide. So let's calculate AA gradient here. AA gradient is a little bit different in this case because so AA gradient here is not patient is not in room here. Patient is on what you call 50%. So the formula is going to be a little bit different. So you're going to put that 0.5 because that was the oxygen times. So 0.5 times 713 713, then you divide carbon dioxide PCO2 divide by 0.8. So that is the big A. So big A is going to be how much? So it is going to be 356 and minus 125. So it is going to be, so that is a big A. So this is big A, which is, so this is a big A, and the what is small a? Small a is equal to, small a is 131, as you can see in the ABG. So A gradient is going to be here. How much? It is going to be, so the big A is how much? Big A is 231, 231, right? 231. So small a is 131. So 100. So that is A gradient. So A gradient is elevated. So whenever A gradient is elevated, you need to think about, so this is alveoli, let's say. So there is something wrong in the alveolar side, like pneumonia, let's say. Either they have pneumonia or there is something wrong in the respiratory membrane here, or there is something wrong in the blood vessel side. Could be, what you call blood clot or whatever. So this patient has a high A gradient. And so to looking at the history, orthopneic patient, and crackles on the exam, so most likely this patient has congestive heart failure, and physical examination is also positive for bilateral crackles, and when they did X-ray, it showed bilateral interstitial edema. So this patient was started on diuretic, and patient did very well. So this is the approach. See how much information you can get by calculating a gradient. So whenever possible, make a habit of familiarizing yourself on a gradient. Very important in a clinical diagnosis. And this concludes the third part of acid-base analysis. Thanks for watching.